Hi, and welcome back to Tactical DevOps. I'm Joe.
And I'm Jane. Today we are taking a look at workloads and scheduling.
Yeah, and this is a really fun one. So I want you to imagine just for a second that you are running the back end for a massive online retailer. And, it's Black Friday.
Oh boy. The ultimate stress test.
Exactly.
Yeah.
So traffic is surging, right? Transactions are firing at like thousands per second. And suddenly, in one of your main data centers, a physical server rack just catches fire.
Like literally catches fire.
Literally. Plastic is melting, the fire suppression sprinklers go off, and 30 physical servers instantly go completely dark. But here's the crazy part. Not a single customer's shopping cart drops.
Wow.
Yeah, the users buying shoes or electronics, they don't even see a loading spinner. The application doesn't just survive, it heals itself in milliseconds, redistributing the work before a human engineer even gets the pager alert.
It's almost like magic when you see it happen.
Right. But how is that physically possible? Well, welcome to our deep dive. We are going to unpack the invisible choreography that makes that kind of technological magic happen.
And it sounds like science fiction when you describe it that way, but it is actually the baseline expectation for modern distributed systems.
Yeah.
Today, we are dissecting the brain of that self-healing architecture. And the source material we're working from is a highly concentrated technical document. It's a markdown file simply titled O2 Workloads-Scheduling.md.
I actually have it pulled up right here. And it looks like a study guide specifically outlining, about 15% of a larger curriculum.
Right.
Based on the references to cluster architecture and, the practice questions at the bottom, this is clearly material designed for a heavy-duty certification. It looks like the blueprint for the Certified Kubernetes Administrator exam, or CKA.
It is the blueprint. But we aren't going to treat this like a textbook, just reading bullet points to you.
Oh, definitely not.
Because the terminology in this document, things like deployments, daemon sets, affinities, taints, these are just vocabulary words. The real value is understanding the philosophy behind them.
Absolutely.
We need to decode the underlying control loops and the mathematical logic that a system uses to manage a fleet of applications across thousands of servers.
So let's jump right into the actual work being done. Because before we can understand how a system schedules applications and, moves them away from burning server racks, we have to define what the applications look like to the system.
Right. The system needs to know what it's dealing with.
Exactly. The source document introduces a cast of characters, starting with the three primary types of workloads. And the very first one on the list is deployments.
Bread and butter.
Yeah. But the guide's definition is incredibly brief. It just says, deployments provide declarative updates for pods.
Yeah, and that single word declarative is the hinge upon which this entire technological era swings. I mean, it is the fundamental difference between the old way of managing infrastructure and the new way.
So the way I usually visualize this is by looking at a high-volume restaurant kitchen.
Okay, I like this.
In the old days, you operated imperatively. You were the micromanaging head chef, standing in the middle of the chaos, shouting specific instructions.
Right. Do this, do that.
Yeah. You'd point and say, turn on that stove, chop those onions, bring me 3 plates. You had to issue step-by-step commands to achieve an outcome.
Which is exhausting.
Super exhausting.
Yeah.
But a declarative system totally changes your job title. You are no longer the yelling chef. You are the restaurant owner who simply writes on a clipboard, I need 3 line cooks at the grill at all times.
Nice.
You hand that clipboard to a kitchen manager, and you just walk away. You don't care what the line cooks are named, and you don't care how the manager finds them. You just declare the desired state.
The restaurant analogy sets the stage perfectly, but let's look at the mechanics of how that kitchen manager actually operates, because that's where the engineering genius really lies.
Right, because a human manager gets tired.
Exactly. A human kitchen manager can get distracted or overwhelmed. But the system we are talking about uses something called a reconciliation loop.
A reconciliation loop?
Yeah. It is a relentless, infinite loop of mathematical comparison.
Break that down for me. What is it actually comparing?
It compares 2 things, the desired state and the actual state. When you create a deployment, you are writing a record into the cluster's central database, which is usually called EECD.
Okay, E on SCD.
Right. That record is your clipboard. It says desired state is 3 copies of the front-end web server. That is all you do. You are finished.
So I just updated the database and walked away?
Yes. Now, the system takes over. A component called the controller manager is constantly querying that database. It sees your request for 3 web servers. Then it queries the actual physical reality of the cluster.
Like taking attendance.
Exactly. It asks how many front-end web servers are currently running. If the cluster just booted up, the answer is 0.
So the controller spots the difference. Desired is 3, actual is 0.
Right. The controller calculates a diff, just like a software version control system. It realizes it is short by 3. So without any human intervention, it generates the commands to create 3 new application instances, which we call pods.
Okay.
Pods, it hands those commands to the scheduler, which places them on servers. A few seconds later, the actual state becomes 3, the loop runs again, desire is 3, actual is 3, the controller goes to sleep.
Well, until the Black Friday fire happens.
Precisely. A server rack melts. One of your front-end web server pods was running on that rack. It dies instantly.
Just on.
A few milliseconds later, the reconciliation loop runs again. It checks the database. The desired state is still 3. It checks reality. The actual state is now 2.
And it doesn't panic.
It doesn't panic at all. It doesn't need to know about the fire or the sprinklers or the hardware failure. It simply calculates the diff. It's short by 1.
Wow.
So it creates a new pod and hands it to the scheduler to be placed on a healthy server. The desired state is restored.
That really explains why the source document describes deployments as providing updates for pods. The pods themselves are entirely disposable.
Completely.
They are the interchangeable line cooks. If one vanishes, the system just spins up a clone. They have no unique identity.
None.
This is perfect for stateless applications, like an Nginx web server, right? Where any user request could be handled by any copy of the app.
Which brings up a critical architectural limitation, because not every piece of software can be treated as a disposable, interchangeable clone.
Right.
And that's why the source document moves immediately to the second workload type, which is daemon sets.
Okay, daemon set.
The definition provided is that a daemon set ensures all or some nodes run a copy of a pod. Basically, 1 pod per node.
See, here is where I struggle with the logic a bit. If deployments are so incredibly resilient and automated, why would I ever restrict myself to running exactly 1 instance on every single physical server?
It seems counterintuitive.
Yeah, like if I need 50 copies of a security monitoring agent, why not just use a deployment? Set the desired state to 50 and let the controller place them wherever it finds room.
Well, think about the failure mode of that approach. Let's say you have a cluster of 100 servers, which we refer to as nodes.
Okay.
You use a deployment to ask for 50 security agents. The scheduler evaluates the cluster, finds 10 nodes that have a massive amount of free memory and CPU, and decides to pack all 50 of your security agents onto those 10 nodes, like 5 per server.
Oh, I see the problem.
Yeah.
I have 90 nodes completely exposed with no security agent watching them.
Exactly. And you've redundantly monitored the other 10 nodes 5 times over.
Which is useless.
Right. A deployment places workloads based on available resources and generic rules. But some software isn't meant to serve the end user. It's meant to serve the infrastructure itself. We call these foundational agents.
So things like logging utilities that scrape error messages off the physical hard drive, or networks procs.
Yes. If you are shipping system logs out of a specific node, the log shipper absolutely must live on that specific node. You cannot scrape the hard drive of server A by running a pod on server B.
That makes total sense.
So a daemon set changes the core scheduling logic. Instead of a global desired state of 50, the daemon set's logic is actual state must equal 1 per qualifying node.
So it's dynamically reacting to the size of the cluster itself.
It is the ultimate welcoming committee. If you add 20 brand new empty servers to your cluster to handle the Black Friday traffic spike, you don't want your web applications landing on those servers before the security monitors and networking proxies are running.
Oh, that would be bad.
Yeah. The daemon set controller watches for new nodes. The millisecond a new node joins the cluster, the daemon set instantly schedules the required agent onto it. It prepares the environment before the regular deployments are allowed in.
Okay, so we have deployments as the interchangeable line cooks and daemon sets as the foundational security guards stationed at every single door. The third workload type in the source guide is the stateful set. And the guide defines this as being used for stateful applications requiring stable network identities and persistent storage.
The key word there is stable. We established that deployments are completely amnesiac.
Right.
When a web server pod dies in a fire and gets replaced, the new pod gets a brand new random name, a brand new IP address, and a totally fresh, empty, temporary hard drive.
Which is a complete disaster if that application is a database.
A catastrophic disaster. Imagine a distributed database like a MySQL cluster or ASCD.
Yeah.
These systems rely on strict consensus algorithms. The nodes in the database cluster need to know exactly who they are talking to. If a database pod named dbnode1 crashes and the system replaces it with a pod named, I don't know, random hash 9384,
The rest of the database cluster will just reject it.
right, the consensus is broken. Furthermore, if that database pod loses its hard drive when it crashes, you've just deleted customer data.
Let's expand on the business analogy. Because if deployments are the disposable line cooks who can share any open locker, stateful sets are the VIP executives of the corporation.
I love that.
The executive demands a specific reserved corner office. That is their stable network identity. If the executive goes on a business trip and returns, they do not get a random cubicle. They walk straight back into their exact corner office.
The stable identity is crucial. A stateful set doesn't generate random hashes for names. It uses a strict ordinal index. If you ask for 3 pods, it names them exactly DB0, DB1, and DB2.
Okay.
And it starts them in that exact order, waiting for DB0 to be fully healthy before it even attempts to start DB1.
So it's highly choreographed.
It has to be. But the identity is only half the battle. What about the filing cabinet in that corner office?
The persistent storage mentioned in the guide.
Right. In a cloud environment, hard drives are often network-attached block storage volumes. When DB0 is created, the stateful set dynamically provisions a specific storage volume and binds it exclusively to DB0.
So if DB0 crashes, what happens to the hard drive? Does it just get deleted?
No, the system actively protects it. The storage volume is detached from the dead compute instance, but it is preserved.
Oh, wow.
Yeah, when the reconciliation loop spins up the replacement pod, it forces it to take the name DB0, and then it goes a step further. It finds that exact orphan storage volume and rigidly reattaches it to the new pod.
It literally resurrects the database node with its memories intact.
It does. And this highlights why stateful sets are so much more complex to manage than deployments. They enforce what we call at most one semantics.
Wait, at most one? What does that mean?
Well, in a deployment, if a node briefly loses network connectivity, the central controller might think the pod died and spin up a replacement.
Okay.
For a few seconds, you might accidentally have 2 identical pods running. For a stateless web server, who cares?
But for a database?
For a database, if you accidentally run 2 copies of DB0 simultaneously, both trying to write to the exact same persistent hard drive, you get data corruption instantly.
Oh, yeah. That's really bad.
It is known as a split-brain scenario. So stateful sets are engineered to be hyper-conservative. If the central controller loses contact with DB0, it will absolutely refuse to start a replacement until it can cryptographically prove that the original DB0 is entirely dead and its storage volume is fully unmounted.
It prefers a temporary outage over data corruption.
Exactly.
This completely changes how you architect a system. You have to interrogate the personality of every single piece of software before you deploy it.
Yes.
If it's a stateless microservice, you use a deployment. If it's a node-level infrastructure agent, you use a daemon set. If it has state, memory, or identity that must be preserved at all costs, you use a stateful set.
That thoroughly covers the what's of our workload cast. But the real complexity and where the source material spends the majority of its focus is the where.
The scheduling.
Right. Once the controller manager decides a pod needs to be created, it hands the definition to the scheduler. The scheduler has to look at a sprawling fleet of thousands of servers and play traffic cop.
Which brings us to the logic of scheduling. Because a cluster of 10,000 servers is far too massive for a human to manage with a spreadsheet.
Impossible.
You can't just keep a mental map of, oh, server A runs the billing app, server B runs the reporting tool. The system needs a way to organize reality dynamically.
Right.
And the foundation of this, the universal glue of the entire architecture, is something the source calls labels and selectors.
Labels and selectors are conceptually simple, but they represent a massive paradigm shift in infrastructure. Google actually learned this lesson years ago when they were building their internal Borg system, which heavily influenced the architecture we're discussing today.
Okay.
You have to decouple the applications from the physical hardware entirely.
So how do labels achieve that?
By turning everything into a metadata query. A label is just a sticky note attached to an object. It is a key-value pair.
Like a tag.
Exactly. You can attach a label to a physical server node that says hardware type equals high memory. You can attach another label that says environment equals production. You can also attach labels to the pods themselves, like app equals front end or team equals billing.
So it's a massive tagging system.
Yes, and the selector is the query engine for those tags. When an internal load balancer wants to route traffic to the front-end web servers, it doesn't have a hard-coded list of IP addresses.
Right.
It just broadcasts a selector query. It says, send this traffic to any pod currently alive that has the label app equals front end.
So the load balancer doesn't know where they are or how many there are. It just trusts the tagging system.
And this applies directly to scheduling. The source guide explicitly breaks down mechanisms called node selectors and node affinity. There is actually a practice question at the bottom of the guide asking, what is the difference between node selector and node affinity?
Let's unpack that. Because if both these features assign pods to specific hardware nodes based on labels, having two distinct tools for it seems redundant. Why the duplication?
It's the archaeological record of the system evolving. Node selector is the legacy mechanism. It is blunt, rigid, and binary.
Okay.
Let's say you have an application that does heavy machine learning inference, and it requires a GPU to run. You would use a node selector in your pod definition that says GPU equals true.
And what happens if the scheduler looks at your fleet at 1,000 servers and sees that every single node labeled GPU equals true is currently at 100% capacity?
The scheduler simply shrugs.
It just shrugs.
Pretty much. It marks your pod as pending, and it sits there doing nothing forever. A node selector is an absolute non-negotiable mandate. If the condition isn't met, the deployment halts.
I can see how that becomes a massive bottleneck.
Right.
What if my application performs best on a GPU, but in a desperate situation, it could still technically function on a standard CPU, just a bit slower?
Right.
I mean, I don't want it stuck in a pending state during Black Friday. I want it running somewhere, anywhere.
And that exact frustration from engineers is why node affinity was created. It is the evolved, highly expressive successor to the node selector. Node affinity introduces the concept of a weighted preference.
The source guide actually uses some truly spectacular technical naming conventions for this. Things like required during scheduling, ignored during execution.
It's a mouthful.
It really is, but it's very descriptive.
The naming is incredibly verbose, but it leaves absolutely zero ambiguity about how the control loop behaves.
No.
The required variant acts exactly like the old rigid node selector. It is a hard mandate.
Okay.
But the second half of that phrase, ignored during execution, is a crucial detail. It means the scheduler only checks the label at the exact millisecond it places the pod on the server.
Wait, really?
Yeah. If someone comes along 3 days later and deletes the GPU equals true label from that physical server, the system does not rip the running pod off the machine. The rule is ignored during execution.
Okay, so it's an entrance exam, not an ongoing background check.
Exactly. But the real magic of node affinity is the other option. Preferred during scheduling, ignored during execution.
The soft preference.
Yeah.
So how does the scheduler actually evaluate a preference? Does it just guess?
No, it runs a highly optimized micro-auction.
And micro-auction.
Yeah. When the scheduler is trying to place a pod with a preferred affinity, it runs a scoring algorithm. It looks at every single available node in the cluster and assigns it a score from 1 to 100.
Based on what?
Based on a combination of baseline fitness, like how much free RAM it has, and the weights you assign to your preferences. You might say, I prefer nodes with GPU equals true, and I give that a weight of 50. I also prefer nodes in the US East 1 data center, and I give that a weight of 20.
That was doing math.
Right. The scheduler calculates the math for every server. A server with a GPU in US East scores a 70. A standard server in US East scores a 20. A server with a GPU in US West scores a 50.
It literally builds a leaderboard.
It ranks them, sorts them, and places the pod on the server with the highest score. But here's the critical part. If every single GPU server is full, their score drops to 0 because they fail the baseline capacity check.
Oh, I see.
The scheduler then looks down the leaderboard, finds a standard CPU server with enough memory, and schedules the pod there. It intelligently compromises to keep your application running.
That is a staggering amount of math happening in milliseconds for every single workload.
It really is.
And all of that node selectors and node affinity is about evaluating the physical hardware. It's the pod looking at the node. But the source material introduces a completely different vector, pod affinity and anti-affinity. This implies the pods are looking at each other.
They are. This is where scheduling moves from hardware matching to true distributed systems topology. Pod affinity is about co-location. It's about applications wanting to be as close to each other as physically possible.
Let's visualize the latency problem. If you have a primary web server that needs to query a specific in-memory caching pod 1,000 times per second, the speed of light becomes your bottleneck.
Exactly.
If the scheduler randomly places the web server in a data center in New York and the caching pod in a data center in Virginia, that tiny bit of fiber optic network latency adds up. Your application grinds to a halt.
Which is why you use pod affinity. You write a rule on the web server pod that says, find a pod with the label app equals cache and schedule me onto the exact same physical server.
So they are practically touching.
Right. The scheduler forces them to be neighbors, so their communication happens over the internal memory bus of the physical server, completely bypassing the external network. The latency drops to near zero.
Okay, so pod affinity is moving in with your best friend. But then we have pod anti-affinity. I usually describe this as refusing to live in the same apartment building as your ex. You want maximum distance?
The relationship analogy is funny, but let's reframe it around the reality of infrastructure failure. Anti-affinity isn't about avoiding bad neighbors. It's about defining your blast radius.
Okay, play that out for me.
Let's go back to your Black Friday scenario. You have a deployment of 3 critical payment processing pods. If you leave the scheduler to its own devices, it might look at a single, incredibly powerful physical server and say, great, I have plenty of room. I'll put all 3 payment pods right here.
And then that specific physical server's motherboard fries, or the power supply dies.
And instantly, 100% of your payment processing capability vanishes.
Oh, man.
Your entire business goes offline. Yes, the reconciliation loop will notice they died and spin up replacements, but you are facing a hard outage while that happens.
So how does anti-affinity prevent that?
You apply a pod anti-affinity rule to the payment pods that says, do not schedule me onto a server if there's already a pod with the label app equals payment running there.
It creates a repelling force field around itself?
Exactly. It forces the scheduler to distribute the 3 pods across 3 completely different physical machines.
Wow.
But it gets even more powerful. In cloud environments, you don't just worry about a single server failing. You worry about an entire data center or an availability zone going offline due to a power grid failure.
Can anti-affinity push them that far apart?
It uses something called a topology key. You can tell the scheduler, don't just ensure we are on different physical servers, ensure we are in completely different availability zones.
That's incredible.
The scheduler will look at the zone labels on the servers and actively stretch your application across geographic regions. If an entire data center in New York loses power, you only lose one of your 3 pods. The other 2, sitting in Virginia and Ohio, seamlessly absorb the traffic.
That is the essence of high availability. You are declaratively engineering your failure domains. You are telling the system how to survive a catastrophe without needing to know when or where the catastrophe will happen.
And the system enforces these rules automatically every single time the application scales up or down.
So we've spent a lot of time on how pods declare their desires. Affinities, anti-affinities, selectors. These are all rules written from the perspective of the application, asking for a specific environment.
Right.
But what if the infrastructure needs to protect itself from the applications? That transitions us into the concept of boundaries. The source document introduces a completely reversed dynamic: taints and tolerations.
This is a vital shift in perspective. Affinities are properties of the pod. Taints are properties of the node. A taint is a defensive mechanism.
I always picture a taint as a physical server deciding to spray itself with a horrific, overpowering perfume.
That's a strong visual.
Yeah. When the scheduler evaluates that server and tries to place a standard pod there, the pod effectively gags and says, absolutely not, I'm staying away. The node actively repels workloads.
The repelling analogy is accurate. The only way a pod can be scheduled onto that node is if it has a specific toleration.
Okay.
To use your visual, the pod needs to be equipped with a gas mask or a plugged nose that is explicitly tuned to ignore that exact brand of terrible perfume.
It's like a bouncer at an exclusive club. The taint is the bouncer at the door saying, nobody gets in without a VIP pass.
Yes.
And the toleration is the VIP pass written into the pod's configuration file.
The bouncer analogy works beautifully for keeping new workloads out, but it falls apart when we look at the specific variations of taints.
Oh, really?
Yeah. The source guide provides a table breaking down 3 distinct taint effects. The exact behavior of the system changes radically depending on which effect you apply.
Let's dissect the table then. The first effect is called no schedule. The guide describes it simply as new pods won't be scheduled.
This is your classic bouncer at the door. If a node is tainted with no schedule, the central scheduler will refuse to place any brand new pods on it unless they hold the toleration.
Makes sense.
But it is entirely forward-looking. If there were already 20 pods happily running on that node before the administrator applied the taint, the bouncer ignores them.
Oh.
They are grandfathered in, they stay running.
So it stops new traffic but doesn't disrupt existing operations.
Exactly.
The second effect is prefer no schedule. The guide says scheduler tries to avoid.
This is the soft limit, similar to the preferred node affinity we discussed earlier. It is a polite suggestion from the node. The scheduler will try its best to place pods elsewhere.
But it's not a hard rule.
Right. If the rest of the cluster is completely maxed out on CPU and memory, and a critical pod needs a home, the scheduler will intentionally bypass the taint and place the pod on the node anyway. It prioritizes keeping the application alive over respecting the node's preference.
That makes sense as a safety valve. But the third effect is the one that seems incredibly aggressive. It is called no execute. And the table explicitly states it evicts existing pods.
This is where the bouncer analogy totally fails. No execute is not a bouncer. It is a fire alarm.
A fire alarm.
When you apply a no execute taint to a physical server, it doesn't just block the door. The local agent on the server actively audits every single pod currently running on its hardware. If it finds a pod that does not have the matching toleration, it immediately terminates it. It massacres the workloads.
Wow, it violently kicks them off the server. Why would you ever want to unleash that kind of chaos on your own infrastructure?
Because sometimes the infrastructure is fundamentally broken. Imagine you have an automated monitoring system that detects the physical hard drive on a server is throwing severe read-write errors.
Okay.
It's going to fail completely in a matter of minutes. You don't want to just stop new pods from going there. You need to evacuate the blast radius immediately.
Ah, I see.
By having your automation apply a no-execute taint, the server essentially declares itself toxic. All the running pods are evicted, the deployments notice they died and instantly spin up replacements on healthy servers, and the failing hardware is isolated and empty, ready for a technician to replace it.
That's brilliant.
And you can even configure the tolerations with a toleration seconds grace period, giving the application exactly 30 or 60 seconds to finish its current network transactions before it gets killed. It is a controlled demolition.
That is remarkably powerful, and this entire concept of taints perfectly answers one of the practice questions at the bottom of the source guide.
Right.
Question number 1 asks, how do you create a daemon set that runs on all nodes, including the control plane?
Well, we need to define the control plane to answer that. In any cluster, there are worker nodes that run the user applications, and there are control plane nodes that run the brain of the system.
The API server, the scheduler, the ECD database.
Exactly.
And obviously you don't want someone's poorly written, memory-leaking web application running on the exact same physical server as the database that controls the entire cluster. It would bring the whole system down.
Right. So when you provision a cluster, the setup tools automatically apply a no-schedule taint to the control plane nodes. The system essentially quarantines its own brain.
Nice.
The taint acts as a protective shield against standard workloads.
Which means, to answer the practice question, if I have a daemon set like a security monitoring agent that absolutely must run on every single piece of hardware, I have to modify the daemon set's configuration. I have to explicitly write a toleration that matches the control plane's specific taint. I give my security agent the highest level of security clearance.
And once you provide that VIP pass, the scheduler allows that specific daemon set pod to bypass the quarantine and deploy directly onto the control plane, monitoring the most critical servers in your fleet.
It's an elegant system of locks and keys. But taints and tolerations are about administrative rules. They don't account for the laws of physics.
No, they don't.
They don't care if a server actually has enough RAM to run the application, which transitions us into the next major subheading in the guide, resource management.
This is where we stop talking about labels and metadata and start talking about hard limits, CPU cores and megabytes of memory.
The source lists 3 distinct concepts under this heading: resource requests and limits, limit range, and resource quota.
Right.
This is where I start to push back on the architecture a bit. Why do we need 3 separate overlapping mechanisms just to manage memory? It feels bloated. Why not just tell the application how much RAM it is allowed to use and be done with it?
It feels redundant until you realize you are managing a multi-tenant environment where developers can and will make mistakes.
Okay, yeah.
It is a defense-in-depth strategy, operating at 3 completely different layers of the system. Let's start at the most granular level, the individual pod. This is where requests and limits come into play.
So what is the difference between a request and a limit for a single pod?
A request is used exclusively by the scheduler. It is the math problem.
Okay.
When you define a pod, you say, I request exactly 256 megabytes of RAM. The scheduler looks at the fleet and eliminates any server that does not have at least 256 megabytes of unallocated memory. It guarantees the pod will have the baseline resources it needs to boot up.
So the request dictates where it can physically fit.
Yes, but the limit is a runtime enforcement mechanism handled by the Linux kernel itself, using something called bring groups. You might say, I request 256 megabytes, but my absolute limit is 512 megabytes.
What happens if the application has a memory leak and tries to consume 513 megabytes?
The local node acts ruthlessly. The kernel intercepts the memory allocation, realizes the pod has breached its limit, and instantly terminates the process with an out-of-memory error, commonly seen in the logs as ohm killed.
It just assassinates the application.
It has to. This is the noisy neighbor prevention protocol.
Right.
If you don't enforce limits, one poorly written looping script could consume 100% of a physical server's memory, starving the operating system and causing every other application on that server to crash. The limit contains the blast radius of bad code to the single pod itself.
I understand how that protects the server, but you said this was a 3-tier defense. That covers the pod level. Where does limit range fit in?
Well, requests and limits rely on the application developer actually configuring them. What happens if a junior developer creates a deployment, forgets to set any limits at all, and just deploys it? Or worse, what if they don't know any better and request 100 gigabytes of RAM for a tiny microservice?
The scheduler will try to reserve it, and it will probably drain the cluster's resources.
Exactly. So cluster administrators use a limit range. This is a policy applied to an entire namespace. You can think of a namespace as a virtual sandbox assigned to a specific team.
Okay, a sandbox.
The limit range policy says, in the billing team sandbox, if a developer forgets to set a request, automatically assign a default of 100 megabytes. Furthermore, the absolute maximum limit any single pod is even allowed to ask for in this sandbox is 2 gigabytes.
Oh, so it intercepts the developer's request before it even reaches the scheduler. If they ask for 100 gigabytes, the API server just rejects the YAML file outright. It says, configuration invalid.
Exactly. It enforces sane defaults and boundaries, preventing administrative mistakes.
So requests and limits protect the physical server from a runaway process. The limit range protects the cluster from a developer deploying a massively oversized pod. So what is the final boss? Why do we need the third tool, resource quota?
Because a limit range only restricts the size of an individual pod.
Obviously.
What if the billing team developer follows the rules perfectly, creates a pod that only requests 100 megabytes of RAM, but then sets their deployment's desired state to 10,000 replicas?
They perform an accidental denial of service attack on the entire cluster. It's the infrastructure equivalent of a fork bomb. The pods are small, but the volume bankrupts the system.
Precisely. That is what a resource quota prevents. It is the ultimate budgetary cap for the entire sandbox.
How does it work?
A resource quota says when you add up all the pods, deployments, and stateful sets in the billing team's namespace, their combined total cannot exceed 50 gigabytes of RAM and 20 CPU cores.
It's the blast store on a submarine. If the team hits their 50 gigabyte budget, the API server simply refuses to create any more pods for them, regardless of how much space is left in the physical cluster.
Right.
It protects the rest of the company from one team's runaway automation.
Layered defense. The individual limit prevents the noisy neighbor. The limit range prevents the absurdly huge pod. The resource quota prevents the volume attack.
So thorough.
It is fascinating how much of this architecture is built around the fundamental assumption that humans will make mistakes, or that code will fail unpredictably. It doesn't hope for the best. It engineers for the worst.
So we have established these incredibly rigid, omnipotent rules. We have declarative deployments, daemon set agents, nuanced node affinities, taints with fire alarm evictions, and a 3-tiered resource defense.
A very tight system.
We have a central scheduler evaluating millions of data points, micro-auctioning nodes, and playing traffic cop for the entire fleet. But then we reach section 4 of the source document, bypassing the rules.
My favorite part.
Because apparently, after building this beautiful, centralized, highly regulated system, the architects decided to leave a massive backdoor open where the normal rules simply do not apply.
This is arguably the most mind-bending and philosophically interesting part of the entire architecture. The guide introduces a concept called static pods.
And the definition provided is incredibly brief. It says, static pods are managed directly by kubelet on a specific node. To understand why this is such a radical departure from everything we've talked about, we need to clarify what a kubelet actually is.
Let's go back to your restaurant analogy. If the central scheduler and the controller manager are the executives looking at clipboards in the corporate office, the kubelet is the local kitchen manager standing in one specific restaurant.
Okay.
The kubelet is a small software agent that runs on every single physical server in the cluster.
And its only job is to take orders from the corporate office.
Under normal circumstances, yes. The central API server sends a command down to the local kubelet that says, start this container. The kubelet starts the container, monitors it, and reports the health back up to the central brain. It's a strict top-down chain of command.
But a static pod bypasses that entirely.
Completely. With a static pod, you don't use the standard command line tools. You don't use kubectl to talk to the central API server. You don't update the etcd database.
Then how do you make one?
You literally SSH into a specific physical server, and you drop a simple text file, a YAML manifest, into a specific directory on that server's local hard drive.
And the local kubelet agent is just constantly watching that directory.
Yes. Usually it's a folder like /etc/ /Kubernetes/ manifests. Every few seconds, the kubelet scans that local folder. The millisecond it sees a new file appear, it says, oh, I guess I'm supposed to run this, and it spins up the pod right there locally on its own server.
And the central brain knows nothing about it.
The central API server has absolutely no say in the matter. It didn't schedule it, it can't move it, and crucially, it cannot delete it.
Wait, it can't?
No. If a cluster administrator sees the static pod running and tries to delete it using kubectl, the central API might briefly remove the ghost representation of the pod from its dashboard, but a second later, the local kubelet will instantly restart it because the physical text file is still sitting on the local hard drive.
That feels entirely rogue. It violates the entire declarative centralized philosophy we just spent almost an hour unpacking.
Yeah.
You have an omnipotent scheduler, and you just built a backdoor that lets anyone with server access ignore it.
Yeah, it sounds crazy.
Why would you ever want to ghost in the machine like that?
Because you have to solve the ultimate chicken and egg problem of computer science, bootstrapping. How do you start the system that manages the system?
What do you mean?
Think about the components we've been relying on this whole time. The kubeAPI server, the scheduler, the controller manager, the etcd database. Those are not magical hardware appliances. They are just software applications.
Right.
And in a modern containerized architecture, they run as pods.
Oh.
Right. The brain of the cluster is made of pods. But if the kubeAPI server and the scheduler run as pods, who tells them to start? You cannot ask the kubeAPI server to deploy itself because it isn't running yet. The cluster is completely inert.
Mind blown. That is a massive paradox.
Yeah. And static pods are the elegant solution to the paradox. The foundational components of the cluster itself, the control plane, have to be static pods.
Okay, I see where this is going.
When you build a new cluster using a tool like kubeADM, the installation tool simply generates the configuration files for the kubeAPI server, the scheduler, and the etcd database, and drops them into that local /etc/ /Kubernetes/ manifests folder on the primary server.
The local kubelet wakes up, operates in complete isolation, reads the local files, and starts the database and the kubeAPI server.
Exactly. The static pods are the spark that ignites the engine. Once the local kubelet brings the control plane to life, the central brain boots up, starts listening for API requests, and suddenly the rest of the cluster can join, and normal centralized scheduling takes over.
That is deeply satisfying to understand. It connects the architecture perfectly.
Yeah.
And it provides the exact answer to the practice question in the guide. Where are static pod manifests stored?
Yeah.
As we just deduced, they cannot be stored in the central database because the database might not be running yet. They are stored locally as raw files on the file system of the specific node where they run.
It is a brilliant piece of engineering. And the source document mentions 2 final edge cases right at the end that also deal with bypassing the default logic: multiple schedulers and manual scheduling.
So not only can you bypass the scheduler with static pods, you can apparently just replace the scheduler entirely. Why would anyone write their own scheduler? The default one is running complex micro-auctions and handling affinities perfectly.
Because the default scheduler is designed to be fantastic for 99% of general-purpose workloads. But what if you were working in high-frequency algorithmic trading? Or what if you were training massive artificial intelligence models across clusters of highly specialized GPUs?
Okay.
The default scheduler looks at CPU and RAM. It might not understand the incredibly nuanced topology of how specific GPU cores communicate with each other over specialized hardware bridges.
So the default math isn't good enough for AI.
Exactly. So the architecture is completely modular. You can write your own custom scheduler application tailored specifically to understand the physics of your GPU hardware.
Oh, wow.
You deploy it into the cluster, so it's running right alongside the default scheduler. Then, in your AI pods deployment file, you simply add a line specifying scheduler name equals custom I scheduler.
The default scheduler sees that line, ignores the pod, and your custom software takes over the placement logic. You have two traffic cops operating harmoniously in the same intersection, directing different types of traffic.
Precisely. And the absolute final mechanism listed is manual scheduling, which is exactly what it sounds like. It is the answer to the final practice question. How do you schedule a pod to a specific node?
Let me guess. You bypass the affinities, you bypass the taints, you bypass the schedulers entirely, and you just hard-code it.
You add a field called node name directly into the pod's configuration file. You say, you will run on node 7, period. The Kube API server skips the scheduling queue entirely and hands the pod directly to the kubelet on node 7.
It's the ultimate imperative override in a declarative system, but I imagine you generally avoid it, because if node 7 crashes, your pod is dead, and the system won't help you reschedule it anywhere else.
Exactly. It's a brittle manual link. But for testing, debugging, or extreme edge cases where you absolutely must force a workload onto a specific piece of hardware immediately, the system gives you the power to pull the manual override lever.
We have covered a massive amount of ground today. We have navigated the entire choreography of how modern applications are placed, protected, and preserved. Before we wrap up, let's do a comprehensive recap of the core concepts, synthesizing everything we've pulled from this source document.
Sounds good.
First, we explored the workloads. We have deployments, the interchangeable line cooks, providing declarative updates for disposable pods, maintained by an infinite reconciliation loop.
Right.
Second, we have daemon sets, the ubiquitous security guards and foundational agents, dynamically ensuring exactly one copy of a pod runs on every single qualifying node, even as the cluster grows.
Which leads to state.
Yes. Third, stateful sets, the VIP executives. They manage stateful applications by enforcing strict, stable network identities and rigidly reattaching persistent storage volumes to survive failures without data corruption.
Then we moved into the logic of placement. Fourth, we decoded labels and selectors, the massive tagging system and query engine that completely decouples applications from physical hardware.
The universal glue.
Right. Fifth, we broke down node affinity and pod affinity, the complex micro-auctions and mathematical scoring systems that attract workloads to specific hardware profiles or co-locate them for low latency, while anti-affinity defines blast radiuses across availability zones.
Then we looked at the defense mechanisms. Sixth, we explored taints and tolerations, the bouncers and fire alarms. They allow nodes to actively repel workloads or violently evict them using no execute to evacuate failing hardware.
Crucial for stability.
Definitely. Seventh, we layered the resource management. Requests for scheduling math, limits for runtime kernel enforcement to stop noisy neighbors, limit ranges to enforce policy, and resource quotas acting as the ultimate blast door to prevent a single team from bankrupting the cluster.
And finally, we uncovered the backdoors. Static pods managed directly by the local kubelet to solve the bootstrapping paradox, alongside the modularity of custom and manual scheduling.
It is a remarkably elegant, resilient system once you see how all the mathematical pieces interlock. And to you listening, why should you care about all of this? Whether you are grinding through practice tests to pass your CKA certification, or you're a developer wondering why your application suddenly killed and restarted on a different server, or you're just genuinely curious about how the backbone of the modern internet survives catastrophic hardware failures, understanding these scheduling rules is the key to mastering distributed systems.
It really is.
You are no longer just looking at a black box. You now know exactly how the central control loops calculate their diffs. You know how to use metadata tags to command fleets of thousands of servers with just a few lines of declarative text.
It truly is an engineering superpower, but analyzing the sheer complexity of this architecture, the affinities, the taints, the quotas, it raises a fascinating question about the horizon of our industry.
What's that?
If this system is already this good at running micro-auctions and automatically managing the physics of hardware placement, are we moving toward a future where human engineers never have to think about nodes or servers ever again? Will we eventually reach a point where we only communicate pure, abstract business intentions to the machine, and the entire concept of hardware scheduling becomes a lost art, entirely obscured and handled by artificial intelligence?
That is a wild thought to leave off on. We started by manually declaring how many line cooks we needed in the kitchen, but maybe tomorrow we won't even need to know there's a kitchen at all. Thank you for joining us on this deep dive.